Okay. Good morning, good afternoon. Welcome to ISQGD SS13 on Ancient Indian Mathematics, organized by the International Society in Quantization Geometry and Dynamics. The ISQGD is an international society dedicated to advancing research and collaboration in mathematics and interdisciplinary sciences. I am also pleased to inform you that a special issue on the same theme is being planned in the Journal of Quantization and Dynamical Systems. We warmly invite your contribution and look forward for your participation. Now it is my pleasure to introduce the first speaker, Dr. Vinod Ghale from D.Y. Patil International University, Pune. The title of his talk is From Vedic Altars to Digital Signature, Baudhayana, Brahmagupta, and Two Paths to Modern Cryptography. Over to Vinod.
Thank you, Swapnil. Thanks to the organizers, for inviting me to give a talk. Thank you. It's a pleasure talking to you. Let me say this, I'm not an expert in ancient mathematics or neither in Sanskrit. But yes, of course, as a community, we are here to discuss our contribution of Indian mathematics ways and the ideas and significance. I'm glad sharing this. Okay. Is my yeah. Okay, so the outline of my talk will be like we will first in the first section we will discuss Baudhayana's ideas, okay, and its connection to one of the unsolved problems like congruent number problem and how it got introduced to the modern tools like elliptic curves, okay, and then in the second section we will discuss Brahmagupta's ideas, okay, and then in the final section we will discuss some modern cryptographical ideas and what are the applications which laid from our ancient mathematics, okay, these pure ideas, this led to the modern cryptographic ideas, okay. Okay, so Baudhayana was like a priest and a mathematician and author of Sulba Sutra, in Indian ancient mathematics, and he was lived like 800 before Common Era. Okay. Okay. So one of his significant work was what is clearly known today we know as like Pythagoras theorem, but Baudhayana knew this and he stated in his work at least 300 years before. Okay. So let me try and then try to pronounce it in Sanskrit like Dirgha Chaturusakshasya Akshanaya Rajju Parshvamani Tirekmani Cheta Prutagabhute Kurudam Tastam Dubhem Karoti. Okay. What he mean to us? Okay. The rope stretched diagonally across the rectangle produces a square which horizontal and vertical sides make together. Okay. That is exactly what Pythagoras theorem is noted as a square plus b square is equal to c square, diagonal square, and he has explicitly listed them. Okay, so few of the examples here listed, and it was not his abstract idea because this Baudhayana and other mathematicians, he was a priest and they were using it for religious rituals. Okay, so they were implementing these geometrical ideas practically. Okay, so and they were aware of this, how to do that, and this Pythagoras theorem, what we know, we were aware before Pythagoras, at least 300 years before, and it has been recorded in a Sulba Sutra. Okay. Okay, he had listed few of the examples. Okay, and we can see the Diophantine equation gets satisfied for these triplets. 3 square plus 4 square is equal to 5 square, and area is half of the base and height is 6. Okay, and later on Euclid gave explicit formulae for generating all the triplets. But okay, but Baudhayana had recorded few of the examples earlier before Euclid. Okay, So coming to this idea, even though this is very simple, straightforward, natural, only any school-going student know this theorem and know this idea of question, there is an interesting problem related to it. Let's discuss that. Okay, which led from the Baudhayana's work. Okay, now we know from the right angle triangle, if there are some sides, okay, which satisfies the Diophantine equation, a square plus b square to c square, and area is half of and base into height. Okay, but there is interesting problem, something called congruent number problem. Okay, and what we call congruent numbers, the numbers which occur as area of a rational right angle triangle. Okay, those numbers are called congruent number. Okay, for example, we have seen 6 is a congruent number, 5 is a congruent number with these sides exactly. And however, n is equal to 1 is not a congruent number 1. However, rational numbers we choose, 1 cannot be produced as the area of rational right angle triangle. Okay, and Fermat proved this. Fibonacci knew this. Okay, but Fermat proved this in the 17th century, and he used this, one of the brilliant ideas of infinite descent method for this structure, for proving this n is equal to 1 is not a congruent number. Okay. Okay, so and we have this explicit transformation, and this is one of the elegant, like we have some Diophantine equations, okay, x square plus y square z square, and area is xy divided by 2. And then we have some transformation, there are some equivalent conditions mathematical. So we can reduce such kind using this Diophantine equation to something called y square is equal to x cube minus n square x. And this is some special form of elliptic curve, something called, okay. What is an elliptic curve, how that rational, the structure on field of rational numbers. In a simple word, over the field of rational numbers, elliptic curves, we can write them after some deductions, okay. Y square is equal to x cube plus ax plus b, and this is of that form. So now this problem now get reduced to elliptic curve form. For example, now as I said, we have this explicit transformation from the sides of the triangle to the points on elliptic curve, and from the points on elliptic curve to the sides of the triangle. Okay, so if we are having that n is equal to 6 area, right? So from that, the sides were 3, 4, 5. So we are having the points on elliptic curve. Okay, we have these methods for that. For the time being, I'm not going to do that. Okay, so in modern mathematics, these numbers which occur as an area of right angle triangle, this is equivalent to existence of a point of infinite order on something called elliptic curves. Okay, that n is associated with this curve x cube minus n square x. This is En for that. Okay, so this is equivalent. N can occur as an area of right angle triangle if and only if that y square is equal to x cube minus n square x, it has a point of infinite order. An interesting fact is, once we are getting the point of infinite order, so we are getting explicit transformation on the sides, and we are keeping on doubling it for each of the points, even though there are infinite points, area, corresponding area will be the same, sides may be different. Okay, so that number is a congruent number. It is very beautiful. Okay, so this problem we know as, like, first we saw this Arabic manuscript, okay, which numbers. The problem is, can we find, okay, do we have an algorithm to determine which numbers are congruent numbers? Okay, the congruent number problem is, do we have an algorithm, or can we decide, given any number, which number can occur as congruent number, which number occur as the area of rational right angle triangle? Okay, this problem is more than 1,000 years old. Okay, first it found in Arab manuscripts, and then Fibonacci worked on it. Fibonacci stated some triplets. He found out some congruent number like 5, 6, 7. These are, he found out sides for that. Okay, and he knew that 1 was not a congruent number. He could not prove, but later, okay, Fermat proved in the 17th century using infinite descent method. Okay, and using this elliptic curve analogy connection, we have made significant contribution. Breakthrough was made due to tunnel. Okay, the tunnel is a mathematician, but he could not prove exactly all the solution. It assumes BSD conjecture, Bern-Schwarz-Dine conjecture. Okay, so the description of congruent number is still open, complete. We do not know, okay, given any number, do we have an algorithm? How to decide that number is a congruent number or not? Okay. There are various ways, there are various researches going on constructing how to rational points of infinite orders and all that. But still, it is open problem. It is dependent on BSD conjecture. Okay. Now there is another well-known mathematician, and he contributed to like Brahmagupta. Okay. He was an astronomer and a mathematician from Vilamala, which is in Rajasthan right now. Okay. And he wrote Brahmasputa Siddhanta. He has made various contributions, okay, treating zero as a number and other contribution in very ancient times. Okay. Like Ujjain was that time a center for like astronomy, like Greenwich today. Okay. Okay. And he was the first mathematician, an astronomer, like who had given this proportionality between integer sides. Okay. For example, if you're having side lengths of integers a, b, c with area n, okay, then he said that there will exist some integers p, q, r such that this side can write in this proportion. Okay, in his book Brahmasputa Siddhanta, a is equal to q times p square plus this proportion we have, and this proof we can see in the Carmichael's work in the modern times. Okay, the theory of numbers and affinity analysis. Okay. Okay, and Brahmagupta gave various formula regarding like cyclic quadrilaterals, where S stands for the semi-perimeter and A, B, C, D stands for the sides of the quadrilateral. Then he gives the area of square root of under root S minus A, S minus B, S minus C, S minus D. Okay, and when the D is not equal to 0, then it converts to the Heron's formula. Okay, Heron again is Greek mathematician from Alexandria, and this is well-known formula for area of triangles. Whenever we know because this formula, it was Heron's formula, they celebrated it very much. Okay, because he was the first mathematician who connected the area number. See, on the left hand side, we are having the area number, and on the right hand side, we are having just sides. So that connection between the numbers, the sides of the triangle and the number, area number. Okay, that connection was established by Heron. So they celebrated it, Heron's formula. But Brahmagupta did it for more general way, in a more general way in ancient times. Okay, why only triangles? He gave formula for the quadrilateral also. Okay, and he worked in various ways. Like one of his were like, suppose we are having some suppose fix some d non-square number, then norm of a comma b for some given ab, a square minus d b square. Okay, and now he given again there's some formula composition law bhavana. What he's saying is norm of a comma b is suppose k and norm of c comma d is l, then norm of ac plus dbd and ad plus bc is k times l. Okay, and now solutions of this, what are the number we're having? That's group law. He defined as AB and CD, the tuples. Okay, he defined that tuple law is AC plus DBD, comma AD plus BC. Okay, this forms a group. Okay, with this solution, well, let's see with some examples. 1 comma 1. Okay, now if we compose this 1 comma 1 with this law, okay, then we get 3 comma 2 here. 1 comma 1 with this law. Okay, and that converts it to 1, and it is called Pale's equation, x square minus 2y square, because we have kept d is equal to 2 here. Okay. 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 This is d is non-square, and what we call fundamental solution, the smallest positive integers. Okay, where it gets solved, and how to find those solutions is like if you're trying 1, 2, 3, we will see where this 1 plus dy square is a perfect square, because just convert x square is equal to 1 plus dy square, and we need that x square number. Okay, and for the larger d numbers, of course, we have other methods by Bhaskaracharya and Jayadeva by Chakravala method. Okay. Okay, for example, for this particular Pale's equation, okay, x square minus dy square. Okay, again, this is also connected to some elliptic curve connection. We have these connections. Okay, now if we are putting this 1 or 2, for 1, it is not a square. Okay, if you put. But when we put 2, okay, then we are having 1 plus it, that is 3 square. So it does get satisfied, and we are getting the solution like 3 comma 2. Okay, 3 square minus, and again it is solvable, it is 1. Solution we are having as 1. Okay. And what is interesting fact about this is, once we are having the fundamental solution, all the solutions, okay, all the solutions are just some powers of these fundamental solutions. Okay, and they form group law, again using this composition law earlier defined. Okay, they form a group and it generates infinite solution, and they form a cyclic group. Okay. Okay. For example, if you just play around with this Pale's equation, we are having this for k is equal to 1, 2, 3. All this gets satisfied. X square minus 2 yk square. Okay. We will have infinite many solutions for each of them. Okay. Now, what we have seen is both of these connections to the elliptic curves. Okay. Just let me recall this. For Baudhayana, he deduced that for rectangles, the sides of uh, and the diagonal side, okay, in the triangle, rectangle, squares, okay. He gave, and we have connection to the elliptic curves in the modern times. Okay, similarly for Brahmagupta's work also we are having, he gave contributed a lot which were known before his time, okay, and he has connected to the elliptic curves here also, okay. And I'm not saying exactly this was the main purpose of what we are doing today in modern ways or something like that, but of course these pure ideas of, like, we could get connected to the elliptic curves, and now the elliptic curves are being used for some different purposes, okay. So somewhere these pure mathematical ideas has led us to some application in modern world. Let's have this, like for example, you have seen Pythagorean triples, area of triangle, and got connected to the elliptic curves. Now if we reduce it to the module P, this elliptic curve, okay, and of course they are finite group, so it gives the elliptic curve discrete logarithmic problem, okay, and we can have this elliptic curve cryptography. So in a simple word, what do we mean by cryptography? Is like for secure communication. If two people want to communicate, this is a science of, or communication, it making this communication secure way. Okay, there are various ways to do it, and we have various methods, techniques to do it. Okay, so one of the ways elliptic cryptography. Okay, and it is being used for many ways. I'll just discuss in the next two slides. And of course, in next we have seen Brahmagupta's formulae, Brahmagupta's Bhavana. Okay, we have these composition, Pale's equations. Okay, fundamental solution, and they're forming cyclic groups. From that, we are able to reduce the discrete logarithmic problems, and we can have this Pale crypto system. Okay, so somewhere these ideas by Baudhayana also and this Brahmagupta also, even they did not, we could not see direct as if their derivations or something like that. But of course, those mathematical ideas, okay, somewhere we could connect to the now led us to some form securing our digital world. Okay, some of this, suppose we are having points, okay, P, and if you are having Q, this is easy. Q times it in the elliptic curve formula. Okay, but what is difficult is, okay, suppose we are having P and Q, and what is there any K times P? Q is there K times P, or P is K times? So that finding K is not easy part. Okay, so we are having elliptic curve, discrete logarithmic problems, Pale crypto system, Diffie element key exchange, digital signatures. Okay, so what do you mean by digital signature and how it is used in the modern? Okay, now, okay, as we have seen something earlier, we have seen elliptic curves like y square is equal to x cube minus n square x. But okay, then there is some American mathematician Koblitz introduced some curves like x cube, y square is equal to x cube plus b. Okay, omitting the x term, constant term. These curves are called Koblitz curve. Okay, so in practice for elliptic curve cryptography, he deduced that, okay, for we can use that y square x2 plus 7, such kind of, okay. FP means finite, T is a prime number, okay, finite field of with prime. So okay, with this finite field structure on elliptic curves, so we can have a stronger system, secure system. Okay, like we can have private key 256-bit integer, public key, security is hard. Okay, we are having this application using Koblitz curve in the elliptic curve cryptography. Okay, one was like if you're seeing Diffie-Hellman, okay, fundamental solution once we're having. So if that Alice and Bob, these are famous characters in the cryptography. Whenever it means in a two-way, two-person wants to exchange some messages. Okay, they send with some A to AP and B sends BP. So this AB both will have, okay, and using that secure system, this is in a vague way Diffie-Hellman works like in a pale discrete logarithmic problem. Of course. Okay. What I want to like example like Bitcoin. This they use elliptic curve cryptography. For example, this Bitcoin they do not have like a base for the currency like we have currency of government or some structure. But Bitcoin is like computer network currency. Okay, they are not secured by something. But whenever we are making a transaction, okay, so each transaction belongs to some that owner. That ownership we have to belong with some using some digital signature. Okay, and that digital signature is being generated by using elliptic curve cryptography. Okay, same works for the whenever sending. We are having various applications using of elliptic curve cryptography in WhatsApp, Apple iMessages. Okay, use government security system, HTTPS. So for securing system, we are using elliptic curves, and these were derived from our simple geometric constructions, which were studied in the ancient Indian mathematics. Okay, people they that time we do not know this elliptic curve system, but of course, those ideas only from the geometric construction, practical approaches of mathematicians, they led us to this script system. And more importantly, we are saying in the last century, one of the important thing was Fermat's last theorem. They used elliptic curve, okay, this to solve that. And those were also derived from the triangle sections. And these are derived from the ancient Indian mathematics. Okay. So that was my try to share a few also Indian some mathematics contributions and how it led to some of the good ideas, very beautiful ideas, and those were very much ahead of time, and they contributed, and it has significance in the modern era also. How it is getting connected and how we are relevant. Those ideas were. Uh, Thank you. That's it from me.
Thank you, Vinod.
Ah.
So let me stop recording.